So let's review what we did in the last previous laboratory. So we unlocked the network depth, that is ResNet architecture. So in the lab, we designed to answer a very important question. It is, if a deeper neural network should be more powerful, why do they often perform worse? So we compare in the laboratory the plain CNN or the ordinary deep CNN and the simple ResNet CNN with residual or skip connections. Both models are almost imported identical for the skip connection, making it fair experiment. So the problem with deep networks, at the first glance, from the more layers, more features learned, and we thought that it's better accuracy. Sounds logical, but in practice, the more layers is more hardware optimization, the vanishing gradients will occur, and the training becomes difficult. Sometimes the deeper network perform worse than the shallower ones. So this is called degradation problem. So the dataset, so we the dataset we use here is we use aerial images. So the classes include things like forest, river, harbor, residential area, other landscapes. So the input image is RGB image, 3 channels, and 100 by 100. So the goal is from image with convolutional neural network and the landscape class. So in the plain block, the first architecture uses a simple convolution block. So the structure is from input convolutional of the 3 by 3, batch normalization, ReLU, convolutional, batch norm, and output. So use the code out is equivalent to f the ReLU self that bn1 and self convolution 1 and its argument is x, and the next out is equivalent to self that bn2 and its argument self that convol 2 argument out. So notice we no skip connection, no preserved input, only the newly computed feature survives. So the plain CNN architectures starts with the input initial convolutional, layer 1, layer 2, layer 3, and classifier. And initial block is 3 channels to 32 channels. So layer 1, 32, and 32 channels. The stride is 1, no downsampling, spatial size remains 64 by 64. And layer 2, 32 to 64 channels, and the stride is 2. And the downsampling occurs, so from 64 by 64 goes down to 32 by 32. Okay, and layer 3 is from 64 to 128 channels, and the stride is 2, another downsample. So from 32 to 32 goes down to 16 by 16. And the final classifier is the feature maps, adaptive average pooling, and flatten. Next to flatten is linear layer, and after that is class scores. And why plain CNN struggles? So layer 1 learn edges, layer 2 learn corners, layer 3 learns textures, and layer 4 learns roofs, and layer 5 learns buildings. As we go over, all the information becomes weaker, and gradient must travel through many layers, leading to vanishing gradients. This makes optimization difficult. So the big idea of ResNet is instead of learning desired mapping that h of x, and ResNet learns the if f of x is equivalent to h of x minus x, and then we reconstruct it. Then the desired mapping is equivalent to fx plus x. So this is a famous residual formula, where x is equal to preserved inputs and f of x is the learned improvement and y is the final output. So the residual block structure is from we input the x, like say we convolutional it, batch normalization and ReLU. After that we convolution again and batch normalization and add them together and perform ReLU and output. Next is save input. So identity equal x. This is the preserved feature map. Next step 2 is the main path, the black one, and the convolution black 2, the output. This compute f of x. Next is step 3 is match dimensions. Sometimes input is 32 channels and output is 64 channels, or 64 goes down to 32 by 32. Those the shortcut cannot be added directly, so ResNet uses downsample, which contains 1 by 1 convolutional and batch normalization. So what does downsample really does? Downsample, except this downsample's argument is x, is used when channel the channel count changes or spatial size changes. Example, if we have the input of 32 by 64 by 64 and the output is 64 by 32 by 30, that's there's a changes happen. So the shortcut must be also become 64 by 32 by 32 before addition. Otherwise, out plus identity would be impossible. So yeah, the downsample layer resizes and preserve input of x, so it can be added to the block output. So why skip connection helps. So suppose we have the f of x is approximately 0, maybe the convolutions learns almost nothing useful. Then f of x plus x becomes y approximate of x. The original feature survives. This is exactly the idea we've been describing correctly. So without ResNet, the output is f of x. If f of x becomes 4, information disappears. With ResNet, the output f of x plus x, even if the f of x is goes down to 0, we still have the output of x, so information is preserved. Next, gradient flow during backpropagation without skip connection. The gradients to the layer, to the another layer, and the layer, and so on layer. It can shrink repeatedly. So with ResNet, we use the gradient and add them together and add. So there is a direct path through the shortcut, so the gradients can flow more easily. This is why ResNet much deeper networks and lifted layers and 101 layers and 152 layers became practical. So simpler ResNet architecture is, the architecture is intentionally almost identical to plain CNN. Initial block, residual stage 1, residual stage 2, and residual stage 3. Then classifier. So the stage 1 is 32 channels, stage 2 64 channels, and stage 3 is 128 channels. So the only major difference is plain CNN uses plain blocks. Simple ResNet uses residual blocks. So the training results, the problem trains plain CNN. Simple ResNet using cross-entropy loss and Adam. And for PyTorch, we had 10 epochs. So expected outcome, the lab explains that the ResNet typically show lower loss. The training loss and validation loss gets lower because optimization is easier. And better accuracy because features and gradients are preserved. Next is more stable training, less fluctuation, better convergence. So here's the key takeaway. Output is given f of x, no shortcut, old features can fade, gradient can vanish, harder to bring, or harder to train deep networks. So the ResNet is output equivalent to f of x plus x, preserves earlier features, provides direct gradient path, easier optimization, enables deep network. So the most important sentence or we did in the entire lab is ResNet does not replace all features with new features. It learns a small improvement of x and adds it to the preserved feature x. If the improvement becomes useless, the network can still rely on original value of x.